So here in this problem, we have to determine that how much energy and the money we are able to save by using a regenerator in the dairy plant throughout the year, and the annual reduction in the entropy generation. And we are given that the volume flow rate of milk we are given as 12 liter per second, and the temperature of pasteurization we are given as 72 degrees Celsius, and the temperature of refrigeration milk we are given as 4 degrees Celsius. And the efficiency of the boiler we are given as 82 percentage, and the effectiveness of the regenerator we are given as 82. It is also 82 percentage, and the cost of the unit cost of natural gas we are given as $1.30 per therm. And to solve this problem, we'll be requiring some input data. That is, the density of milk is 1 kg per liter, and the density of the specific heat of the milk, that is Cp, we have 3.79 kilojoule over kg Kelvin, and we have obtained these value from the table A3. And the density of milk and the density of water is taken to be as same. So this is density of water, and that is equal to density of milk. We are taking it to be as same. Now first, to solve this problem, I will be calculating the mass flow rate of milk, that is m dot for milk is equals to density into volume of milk, volume flow rate for milk. So density we have 1 kg per liter times the volume flow rate we have 12 liters per second. From here we'll get the mass flow rate as 12 kg per liter. Sorry, 12 kg per second. And if you convert this thing into kg per hour, we have to multiply it with 3600. So we'll get 43,200 kg over hour. So this is the mass flow rate for milk. Now we'll be doing the energy balance in for the steady flow system, and in this case we are taking the pasteurization section to be as our system. So we can apply energy balance equation, that is energy in minus energy out is equals to change in energy of the system. Since it is a steady system, so this term would be 0. So we can write this thing as energy in is equals to energy out. So energy in we have Qn plus m dot h1 is equals to m dot h2. From this equation we can write this thing as Qn as this, basically m dot here signifies the mass flow rate of milk times the specific heat of milk times T2 minus T1, and where T2 signifies the temperature of pasteurization, that is Tp, this is nothing but Tp, and T1 it signifies the temperature of refrigeration, that is Tr. So we have to plug all the values in this formula to calculate the energy input to the system, that is Q, and it is equals to m dot we have 43,000, or we can write this thing as, and if we take this thing in 12 kg per second, so we'll write 12 kg per second times Cp we have 3.79 kilojoule over kg degree Celsius times T2 minus T1. So T2 we have 72 minus 4, and this is degree Celsius. So after solving this, we'll get the value as 3093 kilojoule over second. Now if we are using a regenerator that has an effectiveness of 82 percentage, so energy saved, that is Q dot saved, it will be equal to the product of effectiveness times the actual the heat input. So effectiveness we are given as 82 percentage, that is 0.82 times this one is 3093 kilojoule over second. So after solving this, we'll get the value of Q saved as 2536 kilojoule over second. Now, next we will be calculating the fuel saved in the boiler by saving this much of energy. So fuel saved will be equals to the energy saved divided by the efficiency of the boiler. So the energy saved, we have 2536 kilojoule over second, and the efficiency of boiler we have 82%, that is 0.82. So by solving this, we'll get the value as, now we can do one thing also, we can convert the unit also, that one therm we know it is equivalent to 105,500 kilojoule. So from here we'll get the fuel saved as 0.02931 therm per second. So this much of fuel we are able to save per second. And if you calculate the fuel saved throughout the year, so we know in 1 year it is equals to 365 days, and if you multiply it with 24, that means this much of hours, and if you multiply it with 3600, that means this much of second. So the fuel saved throughout the year, this is throughout the year, it will be equals to the product of this one and this one. So we're going to multiply this, and we'll get the value as 924,450 therm per year. So this much of fuel we are able to save throughout the year. Now next I will be calculating the money saved by saving this much of fuel. So money saved will be equals to, and this is for throughout the year, it will be equals to the fuel saved throughout the year times the unit cost. So fuel saved we have calculated as 924 and this is 450 therm per year times the unit cost. So unit cost we are given as $1.30 per year. So we're going to solve this, and we'll get the value as $1,002,800 dollars per year. So this much of money we are able to save throughout the year. So this was the answer for the money saved. Now next I will be calculating the annual reduction in entropy generation. Now to calculate the rate of entropy generation during this process, we'll be applying the rate of form of entropy balance on an extended system that includes the regenerator also. And that means entropy N minus entropy out plus entropy generation is equals to change in entropy of the system. Now since this system is steady, so this term would be 0. Now disregarding entropy transfer associated with fuel, the only significant difference between the two cases is the entropy transfer due to water due to reduction in heat transfer to water, and it is determined by the formula entropy generation reduction is equals to Q out reduction divided by the temperature of surrounding. So this thing we have calculated as 2536 kilojoule over second, and the outside temperature is 18 degrees Celsius, and if you convert this thing into Kelvin, we have to add 273 to it. So after solving this, we'll get the value as 8.75715 kilojoule over second times Kelvin. Now this is the entropy generation per second, and if we calculate the entropy generation reduced, not the entropy generation reduced, so it will be equals to entropy generation, this is throughout the year, this is reduced throughout the year. So entropy generation reduced times the delta T, that is the how much second we are there in a year. So this thing we have calculated as 8.715 kilojoule over second Kelvin times, so we have 365 days in a year times 24, this much of hour times 3600 second, so this much of seconds throughout the year. So after solving this with a calculator, we'll get the value as 2.75 times 10 to the power 8 kilojoule over Kelvin. So this much of the entropy we are able to save per year. This is entropy reduced. So this is the final answer for the given problem. I hope you got both the parts. Thank you so much.